Hi, this is Matt York, and I am going over part A1 for exam 3 and transport 2 for Dr. Coast class. In this problem, I'm going to be performing a Lewis relation to relate heat transfer to mass transfer. So with that, I'm going to start off by defining Null-Sed's number, which in U equals a variable a times the Reynolds number to a exponent b times Prandtl's number to an exponent c. And then I'm also going to define Sherwood's number, which is variable a times the Reynolds number to the power b. Looks familiar, but instead it's going to be multiplied by Schmidt's number to the power c now. So with that, we also have a couple other definitions with the or for Null-Sed's and Sherwood's numbers. So first of all, we're going to just do Null-Sed over Sherwood's number and represent it like that. But we're also going to do Null-Sed's number, which is equal to the heat transfer coefficient times the diameter over the mass transfer coefficient. And then we're going to define Sherwood's number as the definition from the book, of course, which is the what is that? The thermal capacity of multiplied by the diameter over the diffusivity of components A and B. Okay, so with that, we're also going to define Schmidt's number and Prandtl's number based on our definitions of the book. So first, Schmidt's number, SC, is the viscosity, thermal viscosity, divided by the diffusivity of components A and B. And then we're going to do Prandtl's number, which is also, did I see thermal viscosity? I meant, it's not thermal, I think it's kinetic, not thermal, sorry. Kinetic viscosity, I can't spell. But Prandtl's number is also the kinetic viscosity, and this is actually divided by alpha, which represents the thermal diffusivity. So we're just going to put these down so we don't forget what they actually mean. Diffusivity. Okay, so now that we have defined all of these, I should say numbers, definitions from the book that we've shown them, we're actually going to do Prandtl's number divided by Schmidt's number, which, if we go to right here, is equal to, we got kinetic viscosity over thermal diffusivity divided by kinetic viscosity, those cancel out, over diffusivity of components A and B. So we're actually going to have, this is equal to the diffusivity of components A and B over the thermal diffusivity. I always forget what that is. But anyway, from there, this is actually also equal to something else. So what we're going to do, we'll just do PR over SC, and we're going to call this equal to the diffusivity of components A and B multiplied by the density, which is also multiplied by the heat capacity over the, I forget what this variable is. I know it's K, but it's, the mass transfer coefficient. Okay, so with this, we actually can solve this problem. So I'm actually going to roll my paper up because I don't want to miss anything. Okay, so we're actually given in this problem a couple things. So I'm going to go and look at this problem, or well, not this problem, in the book, we're given a couple things. So we're given that the mass transfer coefficient is 0.03 watts per meters times Kelvin. Density is 1.2 kilograms per meters cubed. Oh, that does not look like kilograms. 1.2 kilograms per meters cubed. And then our heat capacity is 1,000 joules per kilograms times Kelvin. And our diffusivity of A and B is 3 e to the negative third meters squared per second. Okay, so knowing these things, if we put these four numbers into this equation, we actually are going to get a number very close to 1. And what this equation actually also represents, if you can see that, is 1 over the Lewis number. So if 1 over the Lewis number is approximately equal to 1, that shows us that the mass transfer over the heat transfer is approximately 1 related through this Lewis relation. Thank you very much, and part 2 will be in momentarily. Okay, so now in part 2, we are going to use this Lewis relation that we discovered in part 1 to determine the relative humidity of wet and dry bulb temperatures in an energy balance system. So we're actually going to start off with an equation with the heat of vaporization. Heat of vaporization, just so we don't forget. Vape, I'm going to call it. Heat of vaporization multiplied by the thermal conductivity, which is then multiplied by the concentration of water at the surface level, subtracted by the concentration of water, no, that's the temperature, the concentration of water at a spot very far away from the surface level. And we're going to set this equal to the heat transfer coefficient multiplied by the temperature of water very far away from the surface, subtracted by the temperature of water at the surface. Okay, so really quickly, before we move on with this equation, we're actually going to define another thing so we can make a substitution for these variables. So the heat transfer coefficient divided by the thermal conductivity is equal to the density multiplied by the heat capacity. So knowing this, we can actually divide the, oh, sorry, this is a little bit out of focus. Here, I'm going to fix that really quick. So knowing this, we can divide the thermal conductivity over to this side, and we'll get the heat transfer coefficient over the thermal conductivity, and we can substitute this in. So if we divide both sides by thermal conductivity, then we get heat of vaporization multiplied by the concentration of the water at the surface level minus the concentration of the water at a spot very far away from the surface level is equal to the density multiplied by the heat capacity, times the temperature of water at a spot very far away from the surface, or subtracted by the temperature of water at the surface. Okay, so knowing this, we actually now can substitute pressure in for, or partial pressures in, rather than these concentrations. So we're going to do the partial pressure, well, heat of vaporization multiplied by the partial pressure of water at the surface, subtracted by the partial pressure of water spot very far away from the surface. That's a comma, sorry. Oh, we're just going to do that. Okay. And this is going to be divided by the coefficient R and temperature. Because in an ideal gas situation, we know PV equals, or well, not ideal gas situation, but we know that P over RT can translate here for the concentration. Anyway, so then we're going to do this is equal to the total pressure multiplied by what we had earlier, the temperature, again, of the water far away minus the temperature of the water at the surface. And this is also going to be divided by RT. Well, these are clearly just going to cancel out, but as we cancel that out, we have to multiply this total pressure by the heat capacity again. So knowing this, we actually are going to, and you know what? I didn't say, really quick, I just realized after doing this. So this temperature right here is the average temperature of, the average temperature between the surface and a spot very far away from the surface. We could do times temperature at the surface and temperature very far away from the surface, but it's just easier if we just do average. So I do want to add that because that is very important to this problem. But going off of this, now that we cancel this out and add the heat capacity back in, we have the relative humidity. Oh, I don't know if you can see that at this point. I'm going to slide this up a little. The relative humidity is equal to the pressure, the pressure at the surface divided by the pressure of the saturation with the temperature being that of water at the saturation point. Thank you very much. Part 3 will be coming soon. Hi, this is Matt York, and I am doing part 3 now for our third exam. So in this part, we are going to be relating the adiabatic saturation temperature to the wet bulb temperature. So using some of our relationships in the first 2 parts of this, we're going to actually be able to figure out the relative humidity equation we've already solved, but we're going to show how it relates through these adiabatic and the wet bulb temperature. So first off, I'm just going to describe this equation. So we have a surface, I should say, with water running through right here, down here at the bottom. This is water, and this is air. Right to the tube at the top. And this tube is insulated, so I'm going to go like that on the outside of the tube, just to show we have some insulation. Okay, so, it is blurry again. Okay, so we have, a mass flow rate of air and a temperature in. And out, we have a temperature out. We're also going to have a pressure out and a pressure in, the beginning of it. And this, again, is H2O. We'll just label that. Okay, so getting into this equation, we're actually going to look at the enthalpy in and the enthalpy out, and we're going to set these equations equal to each other. So starting off, we know the enthalpy in. The enthalpy in has the mass flow rate of air multiplied by the heat of vaporization, which is also multiplied by the pressure of water in, and that is multiplied by the molecular weight, because we are going to have, that helps us get our units correct, if you will. So then from there on, we're going to divide that by RT, and which is our, this is the molecular weight of water, I should say, and R is the coefficient in the ideal gas equation, and temperature is just the temperature in on this side. So then this is multiplied by RT divided by the total pressure, and that is multiplied by the average mass. Or wait, not mass, sorry, average molecular weight through this tube. Average molecular weight. There we go. And going forward through that, we also have to add our heat capacity multiplied by the temperature in. And you know what? I actually made a mistake. I'm realizing this is the temperature in. This is just the overall temperature of the two. Okay, so we're also going to do the enthalpy out here. And everything is going to remain the same. So I'm just going to do this really quick. Mass flow rate of air multiplied by the heat of vaporization. And the only two things that are going to change, one of them is the partial pressure of water. This is the partial pressure of water out. And this is multiplied by the molecular weight, again, for unit purposes, divided by RT. And then this is multiplied by RT, divided by the total pressure, multiplied by the average molecular weight. And the only other difference is the heat capacity is multiplied by the temperature out. So there's only two differences, the partial pressure of water and the temperature out. So going from there, we're going to set enthalpy in to enthalpy out. Well, we have the mass flow rate of air on both sides. We have the heat of vaporization on both sides. You know what? Actually, we can't cancel out the heat vaporization. Oh, because it's multiplied by something that's different. Okay. Actually, sorry, I'm gonna rewrite that. We do need these heated vaporizations, but we can cancel out the mass flow rate of air in. We're gonna obviously need the pressure, the partial pressure of the water in and out, because those are different. And then these RTs we were actually allowed to get rid of as well, because they're on both sides. And oh no, sorry, not because they're on both sides. It's actually because we have RT times RT right here. And then we're going to keep total pressure, mass average. Oh, you know what? I actually made a mistake here. This average mass. Oh, no, okay, I didn't make a mistake. It's on the denominator. It should be. Okay. Yeah, that's good. Okay. I thought I made a mistake there, so I think we're all good. So, yeah, I just need to add that. That's what you do. Okay, cool. Just to make myself a little clearer, I like to get my algebra right a little bit. All right, anyway though, so that simplifies this equation down to the heat of vaporization multiplied by the molecular weight of water divided by the partial pressure, I think it's the total pressure, not the partial pressure, my bad. The total pressure multiplied by the average mass throughout this, and then this is multiplied by the pressure of water in minus the pressure of water out, which is just the partial pressure of each situation, and this would be equal to the heat capacity multiplied by the temperature out minus the temperature in. Beautiful. So, going forward on that, we now are going to put these pressures into concentrations. So, as we did in part 2, we're going to get rid of this pressure total and mass, average mass, molecular weight, sorry, not mass, I keep saying mass, molecular weight, this average molecular weight, and because if we are looking for concentration and we multiply these by this, we actually can cancel this out, these will become concentrations, which would be the concentration at the surface and the concentration far away from the surface. The other thing we need to do though, if we want to be able to make this work, we have to multiply this side. Well, both sides. We're multiplying both sides by the density because that's how this cancels out. If that makes sense. So what we get is molecular weight of water multiplied by the heat of vaporization times the concentration at the surface minus the concentration far away from the surface is equal to the heat capacity multiplied by the density, okay? And that is, again, still just, oh, well, no. Instead of our out and our in, we have the surface and we have the far away from the surface. So we need to be of far away from the surface minus at the surface, which would be just water. Okay, so actually at this point, what we're going to do, I don't even know if you can see it. I'm going to bring this down, okay? At this point, what we're going to do is we are going to try to put this into back to the pressure at the saturation point, not the partial pressures as we did earlier, but the saturation point. So we're going to do heat of vaporization multiplied by the molecular weight, not mass, of water. And this is going to be multiplied still by our concentration in the surface minus our concentration far away from the surface. And that's going to be equal to, this is actually going to be our total pressure multiplied by our molecular weight, our average molecular weight, I should say, all divided by RT. And the reason we're going to, sorry, okay. I'm getting ahead of myself. And this is multiplied by temperature far away from the surface and the temperature at the surface. Okay. That should be nice. Okay. So the reason we're doing this is we have to multiply both sides by this if we're going, well, sorry. We want to put the heat capacity and the density in terms of pressure, which is what we just did here. We just convert it into pressure, because then we can get the saturation, or the pressure at the saturation point. So what we're going to do now is, by doing that conversion, we get heat of vaporization times the molecular weight of water times the pressure at the saturation point of water at a temperature, at the surface temperature, sorry. And that is actually going to be subtracted by the pressure of water at a spot very far away from the surface temperature, or for surface point, I should say. So this is all going to be divided by RT, because again, if we're getting into pressure, we have to do RT to get back into pressure. And we're going to set that equal to the total pressure multiplied by the average mass, common theme here, not divided by, multiplied by the heat capacity, which is multiplied by the temperature at a spot far away from the surface minus the temperature at the surface. And now, if we use algebra to manipulate this equation, because we got pressure, right? Total pressure. And we said, we're going to move this from concentration back into partial pressure, but this time it's going to be the saturation point. So we're going to divide it by RT, and we're going to add heat capacity back over here to get all of our units correct. And now we're going to flip it, because that's going to get us right to our relative humidity. So heat of vaporization times molecular weight, this is the pressure of water at a spot far away from the surface, subtracting the pressure at the saturation point of water at the temperature at the surface is equal to, I didn't do over RT is equal to the total pressure times the average molecular weight, I keep saying mass, average molecular weight, times the heat capacity, and then the temperature at the surface minus the temperature at a spot far away from the surface. And that gets us back to the relative humidity being the partial pressure of the water at a spot far away from the surface divided by the partial pressure of the saturation point of the water at a spot far away from the surface. And that is, this is supposed to be far away from the surface. My bad. That's what would have gotten us wrong. Anyway, a spot far away from the surface, getting us our answer from part 2, but showing how we can relate the adiabatic system to a wet bulb, or adiabatic temperature system to a wet bulb temperature system, and this is still that same relationship that we found with relative humidity. Thank you very much. I hope you enjoyed this video, and have a great rest of your day.